Bismillah ar-Rahman ar-Rahim. This is the second video lecture on quality control for third level clinical pharmacy student, Dr. Abdulrahim with you, to continue our talk about quality control procedures of herbal drugs. Last time we defined quality as the drug to be effective and safe. There are 3 steps to assure the efficacy and safety of herbal drugs. First, the identity, proper identification of these herbal drugs. Secondly, to make sure that they are pure and devoid of adulteration and toxic residues. And we are in this point talking now to continue the procedures which affirm or confirm the purity of herbal drugs. Last time we talked about foreign matter, moisture determination, ash values, and so on. More testing or more experiments performed to confirm the purity of herbal drugs as crude fiber determination. The crude fiber is a means for concentrating the more resistant cellular material of drugs for microscopic examination, particularly applicable for rhizomes and bulbs, which contain large amounts of starch and resins. The steps involved in this technique are defatting of the powdered herbal drug, followed by boiling the herbal material with standard acid and standard alkali with washing in between. The crude the fiber determination is useful to inspection of foods and also can be used in to detect the presence of adulteration in some drugs, like for example the presence of clove stalks in clove. In this case, actually, the crude fiber figure will be higher. Also, one of the experiments performed to achieve purity of herbal drugs, tannin content. This experiment is performed for tannin-containing drugs such as hamimelis, which is commercially used as a source of tannins. The assay is made using the high powder method, as you know from phytochemistry 1 course, and also by calorimetric assay using reaction with sodium phosphomolybdotungstate reagent. One more experiment is bitterness value. The bitterness value is performed for drugs which have bitter taste, such as Centauri, Ginger, and Wormwood. These drugs have their therapeutic effect based on the bitterness. The bitterness value is determined here organoleptically by comparison with standard solution of quinine hydrochloride. Swelling index. This experiment is made for drugs which contain mucilage, and this index is defined as the volume occupied by 1 gram of the herbal drug and its adhering mucilage after allowing to swell in water for 4 hours. To perform this experiment, 1 gram of the drug is put in a measuring cylinder or graduated cylinder and treated with 1 ml of 96% ethanol and 25 ml of water, and stirred for every 10 minutes for 1 hour and then allowed to stay for 4 hours. The volume occupied by the drug is defined as the swelling index. For example, agar has a swelling index of 10, means 1 gram of agar after this experiment will occupy 10 millimeters, will exhibit or display a volume of 10 milliliters, and so on. The experiment can be performed on the whole drug, like in case of linseed and psyllium, because in these cases the psyllium, the message is present in a layer near the surface of the drug. In other instances, such as in marshmallow, the message is distributed throughout the whole drug, and in this case we can make the experiment on powder drug. Other procedures to measure the swelling power of the herbal drugs may include or involve variations in the procedure, and also we hear about terms such as swelling factor, swelling power, swelling value, and so on. Toxic residues, we talked about this factor before, and they mainly include the detection of pesticides, which we are obliged to use during cultivation and storage of herbal drugs, as well as the presence of mycotoxins such as aflatoxin and also radioactive impurities. Similar problems of these toxic residues are encountered in food industry, but it is much more serious problem in foods than in herbal drugs. Many spices and drugs are allowed to contain pesticides to a certain or acceptable level. Techniques to measure or to estimate these toxic residues may use fluorescent chromatography and GLC and HPLC, depending on the concentration. For example, GC and HPLC are more sensitive and used to trace small amounts of these organochlorines or urea derivatives. However, the procedure or the procedure for preparation of therapeutic doses of herbal drugs using infusion, for example, minimizes the level of toxic residues or the amount of the toxic residues present in the dose. Also, this can be also avoided, or the presence of toxic residues can be avoided by extraction of the active constituents. It was found also that ethylene oxide, which is a very potent bactericide and insecticide agent, and also very toxic because of its conversion to ethylene chlorohydrin, can undergo decomposition or can be reduced by storage at 30 degrees centigrade. The third important step to assure the purity or the efficacy and safety of herbal drug is the content or assay. This is the most difficult experiment to achieve, because in most cases there is no known clear active constituent of herbal drug. Sometimes we may use markers, certain markers, to assay these herbal drugs, and some experiments may also tend to estimate total content of particular active constituent. For example, total alkaloid content in belladonna or total glycoside content in digitalis. However, sometimes not all these compounds are the active agents. For example, in case of raol fuels, only reserpine and reserpine are the active hypotensive compounds, and therefore the total alkaloid content is not indicative of the efficacy of the drug. the important estimation here is the estimation of reserpine content, which is a major hypotensive compound. Recently, biological assays have been replaced by chemical assays. If the total of the active constituent is not known and there is no marker to assay the drug, in this case, the assay is made in the percentage of extractable matter with particular solvent. The choice of the solvent depends on the nature of the compounds present in the drug, and this can be deduced from the traditional use. For example, in most cases, crude drugs or herbal drugs are used to make a tea. And in this case, hot water soluble extractive expressed in milligrams per gram of air-dried material may serve as content or assay. For volatile oils, which are present in many medicinal plants or crude drugs, a special assay is used to measure its volume and its yield in the herbal drug is by steam distillation. Using steam distillation, using a Clevenger apparatus. This is sketch for Clevenger apparatus in which we mix the herbal drug with water in a flask, which is attached or fitted into this apparatus, and heating on water bath or heating mantle or sand bath. In this case, the oil will co-distill with water and condense and will be separated as a layer in this graduated tube. This version of Clevenger apparatus is used to determine the percent of oils lighter than water, because the oil layer will be floating. It's lighter than water. While the water collected in this graduated tube will be returned back into the distillation flask. For oils heavier than water, we use the tube a different design with tube having different orientation, so that the water will be returned into the distillation flask, where the oil heavier than water will be collected in this graduated tube. If the active constituent is known, in this case there are many assays which can be performed, such as ketoconazole, for example, can be assayed by calorimetric assay using alkali hydroxide, and so we can use different methods for the assay of these known active constituents, such as chromatographic methods, cellular chromatography, HPLC and GC, spectroscopy method, UV visible spectroscopy or mass spec, or use of combination of chromatography and spectroscopy techniques such as GCMS or HPLC-MS. And recently, tandem mass spec was used to assay or a target compound in a complex mixture of plant constituents. Immunoassays were also used to estimate particular compounds. It's marked by being highly sensitive and very specific, such as a radioimmunoassay and enzyme-linked immunosorbent assay. It's basically used for quantitative determination of many compounds in biological fluids. Refractive index is used for the detection of the purity of volatile oils and fixed oils, so used mainly for liquids. Refractive index is the sign of angle of incidence or divided by the sine of angle of refraction, usually performed at temperature 20 degrees centigrade and using certain blends of sodium D-line sodium D-light at 589 nanometers, because it is affected by the temperature and the wavelength of light, the wavelength of used light. The instrument used to measure the refractive index is the Abbe refractometer, and more recently we have automatic refractometers called Leica Abbe, Auto Abbe refractometer. It is used for measuring the refractive index of oils, volatile and fixed oils. For example, you can differentiate or detect the adulteration of cinnamon oil by other oils such as cassia oil using this measurement. Optical rotation. It is the angle of rotation of plane polarized sodium D-light when passes through sample of liquid placed in a sample tube of a polarimeter. The magnitude of the optical rotation depends on the thickness of the examined layer, on the temperature, and on the also the wavelength of the light or the nature of the light employed. Usually, it is measured using also sodium D-line or sodium light at 589 nanometers at 20 degrees centigrade. It uses long sample tube of in decimeters. However, modern polarimeters we can use tubes 1/10 the length of sample tube of visual polarimeters and with accuracy of 0.01 degree. Many compounds, volatile oils, and material are optically active or have coherent centers because they are formed in plant by enzyme reactions. The solutions of these compounds is prepared in ethanol or chloroform. The value obtained should involve the solvent used, also the temperature and the wavelength of the light used in measuring of the optical rotation. So, quantitative chemical tests. These are chemical tests devoted to examination of fixed oils, basically, such as acid value, iodine value, saponification value, ester value, unsaponifiable matter, acetyl value, and volatile acidity. However, some of them can be applied also to test the or to assay other drug types, such as the use of acid value in assay of resins. Some resins may contain acids such as chlorophene, for example, which contain acetic acid. Balsams also, which contain cinnamic acid or benzoic acid. We can measure for this balsams acid value, ester value, and saponification value because they contain esters of these acids. Volatile oils also may contain alcohols, may contain esters, and so we can perform acid value, acetyl value, and ester value for these volatile oils. For gums, for example, sometimes we can estimate volatile acidity. These are some definitions of these quantitative chemical tests. The acid value is defined as milligrams of potassium hydroxide required to neutralize 1 gram of chemical substance. It's basically fixed oil, but it can be other type of chemical material or chemical substance. This is the measure of free acidity, free acid present in the 1 gram. Iodine value or iodine number or iodine index. It is a mass of iodine in grams consumed or absorbed by 100 grams of chemical substance. It is used usually to assay unsaturated fatty acid. Saponification value, milligrams of potassium hydroxide required to milligrams of potassium hydroxide required to neutralize free acid and estimate the ester or saponify the ester present in 1 gram of chemical substance. The ester value, therefore, is the difference between saponification value and acid value. Acid value for free acid. Saponification value of free acid and the ester. Ester value is the difference between saponification value and free acidity or acid value. Unsaponifiable matter refers to those substances present in the oil or fats and not saponified by alkali hydroxide, and they are extractable with ether, such as sterols, for example, such as sterols or long-chain hydrocarbons or sometimes alcohols. Acetyl value is determined to estimate the number of hydroxyl groups present in the substance. For example, in oil of menta, volatile oil of menta, we have menthol, we have menthone, we have methyl acetate. Methyl acetate can be assayed by the use of ester value. Menthol can be assayed by esterification of menthol into methyl acetate and total ester determined, and in this way we can estimate how much menthol is present. Also, the other additional methods for assay include spectroscopic methods. IR spectroscopy was used to assay pyrrolocarbene and physiostigmine by comparison with reference substance. British Pharmacopoeia also uses UV spectroscopy to assay morphine in opium, and another C in digitalis or other pharmaceutical formulations. Fluorescence spectroscopy was used also for compounds which have or display fluorescence. As you know, quinine and cinchona alkaloids in presence of acid, oxygenated acid, show fluorescence character and can be assayed using fluorescence spectroscopy. Or NMR spectroscopy also was used to assay some drugs, although it is used or applicable for structural elucidation. However, H1NMR was used to assay atropine, for example, in extract of belladonna, and later on we will talk about quantitative NMR, the new trend for assay of medicinals. Tandem mass spec. This type of mass spectroscopy uses two mass analyzers. Mass spec usually is used or associated with the structural elucidation of organic compounds. However, by using of two mass analyzers in series, we can assay target compound in very complex mixture with very high sensitivity, estimated in picogram amount. This type of assay is marked by high sensitivity and similar in sensitivity almost to the RIA, but it's much more faster than RRA, or more rapidly performed. It was used for the assay, for example, of cocaine in coca leaves, plant material, assay of pyrazine alkaloids in sinecio, assay of taxol or toxins in the plant material of Taxus species, needles of Taxus species, also, for example, aflatoxin, which is a mycotoxin, and peanut butter. Botanical extracts. Botanical extracts, these are a form of drugs which are not present in the form of liquid extracts, not in the form of plant material, such as, for example, extract of ginkgo, extract of echinacea. These are available in the form of extracts. In this case, we cannot examine drugs based on their morphology or microscopic characters. Therefore, we inspect we have form of this botanical extracts called standardized extract. Standardized extracts are high quality extracts containing consistent levels of specified compounds. They should be subjected to strict quality controls during all phases of preparing the plant for extraction, for example, growing, harvesting, and even also in the manufacturing process. In preparation of plant extract, it should be prepared from the specified organ because different organs of the same plant may have different constituents and produce different effects. For example, in Urtica oryens, the aerial parts of the plant are used to treat rheumatoids or rheumatism, whereas the roots can be applied for treatment of benign prostatic hyperplasia. If the active constituents of these extracts, basically if the active constituents are known, we can apply different chromatography techniques to assay these extracts. HPLC, gas chromatography if there are volatile compounds, or use of a combination of gas chromatography and spectroscopy. But if they are not known, in this case we assay the drugs based on a marker substance present in the extract. The marker substances are not the active constituents of the drug, but they are chemically defined compounds. Their level probably guarantee the activity, but they are not themselves the active compounds of the extract. It's ideal if the markers are also the active constituents, but however, this is not often the case. There are two categories or two types of standardization of these extracts. First category, true standardization, means that the extract contains defined amount of the active constituents. For example, the ginkgo biloba extract contains 26% of ginkgo flavones and 60% of ginkolioids or diterpenes, which are the active agents. This type of extract was subjected to true standardization because the active constituents are present with a different amount. The second category of the extracts or standardization are based on the extracts containing a certain percentage of marker compound. These markers are not indicators of the therapeutic activity or quality of the herb. Total quality assurance of herbal medicine require multiple methods, for example. Good manufacturing practices. In case of synthetic compounds, this is enough. GMAP is enough for synthetic compounds. Good manufacturing practices. Okay, but in the case of herbal drugs, this is not enough because the source is living, or plant material is a living source. It should be subjected also to good agricultural practice or GAP. This means that we have to ensure the whole cultivation process from the field collection to post-harvest processing is standardized. This GAP process is aiming at ensuring the quality of the raw material, which will be subsequently used to prepare the therapeutic form of the drug. Hurdles to authentication and quality control of medicinal plants. Hurdles means obstacles or barriers or difficulties for authentication of the quality control of herbal drugs. These hurdles are not present or encountered in case of drugs based on synthetic compounds. The first problem in authentication and quality control of medical, and we discussed that before, is the lack or absence of clear botanic identity of some traditional medical herbs. We are not sure of the classification or botanical source of these herbal drugs. The second problem is that we do not know, usually, in most cases, clear active components are not known in most herbal or many herbal drugs, so that we can make proper assay on them. The third is that when we make bioactivity target, it's not easy because we do not know which constituent is responsible for the activity. This beside the safety issues. Other safety issues, the risk of presence of extrinsic and intrinsic risks or factors, which can be in the form of adulteration or residues likely to be present in the plant sample. There are advances which happened lately in the field of quality control of herbal drugs, including DNA fingerprinting, analysis of active and marker compounds, chromatographic fingerprinting. As we said before, if you have active constituent, non-active constituent, even a marker, we can make an assay and we can make evaluation based on the level of these compounds in the plant. However, this does not give a complete picture because multiple components or other components may also be involved in the therapeutic effect of the drug. Therefore, we use chromatographic fingerprinting. Chromatographic fingerprinting to identify the quality, for identification and quality control of medical herbs. Fingerprinting actually provides chromatographic profile of the whole compounds present in the drug. HPLC is the most convenient to perform chromatographic fingerprinting. Chromatographic fingerprinting became one of the requirements proposed by US FDA or Food and Drug Administration for botanicals and also by European Agency for the Evaluation of Medicinal Products. We will talk now about the quality control of one of the herbal drugs which was extensively used therapeutically, which is ginseng, Panax noto ginseng. The wide therapeutic or trade in this of ginseng reaching about $300 million annually motivated research on the quality control of this drug, which is subject to adulteration, and there are many species of ginseng available. This motivated research to make designs for new experiments for quality control of this herbal drug. Basically, the bioactive components of this drug are the ginsenosides, which are steroidal triterpenes. Many of them are present in the ginseng, but the activity of these compounds differ based on the glycan and sugar part of the glycoside. In some instances, the probably pharmacological activity of the individual compounds may work in opposition. They have opposite effects. There are two forms of Panax noto ginseng, with the Chinese ginseng, raw and steamed form. Traditionally, the raw form is widely used because of its cardiovascular action. It has arrest bleeding, or the drug arrests bleeding, disperse blood clots and improve blood circulation, also decrease or disperse bruises and alleviate swelling and pain. Furthermore, the drug was found to decrease blood pressure and can be used for treatment for experimental heart ischemia, and they may have antiarrhythmic effect. This is the raw ginseng. The steamed Panax noto ginseng, this is frequently used and claimed to be able to nourish blood to increase production of various blood cells in anemic patients, and to be used by weaker patients who cannot tolerate the uptake of the raw form of the herbal drug. Most of the research now is focused on the raw Panax noto ginseng. There is a problem of the quality control of the steamed ginseng because of different actions, because even there is no standard method for steaming of the raw Panax noto ginseng. Due to the different actions of and the clinical indications of steamed and raw ginseng, using wrong form of the herb may lead to undesirable results. The extensive research on this drug led to development of different quality control experiments. First, DNA fingerprinting, chemical fingerprinting, including chromatographic fingerprinting, and the use of a modern FTIR spectroscopy as a technique to unveil the quality of the herbal drug. DNA fingerprinting was used as to replace the macroscopic and microscopic means to identify the herbal drug, because the macroscopic and microscopic means of evaluation has the following disadvantages. First, it's subjective and depends on the evaluator. There are closely related adulterants or properly related species are very similar to the original drug cannot be differentiated based on morphologic and microscopic examination. Also, sometimes very difficult that herbal drugs in powdered form or in slices can be examined by this method. DNA fingerprinting, therefore, is used to identify different species. This is called genetic analysis. Genetic analysis. It is independent extrinsic factors such as the cultivation, the age, and the processing method of the plant. And it detects the nucleic acid of the plant. This is not subject or not different, is not affected by these conditions. Therefore, this genetic analysis or DNA fingerprinting procedures was used to differentiate between species and identify their adulterants.